Okay, well, first of all, just to welcome everybody to this evening's meeting. Obviously, with the COVID situation being somewhat fluid, I'm very grateful that we have our Zoom account so that we can at least hear our wonderful guest speakers, either at the mills when things permit or on Zoom. So at least we don't miss out. I hear there's a suggestion of a clear sky later tonight, so anybody who actually wants to have a look at it might actually have a chance of seeing something later on, which would be pretty unbelievable. There are only a couple of things I wanted to mention. One was if people still have their subscriptions to pay, if they could send these to Graham McAteer, along with any requests for the Society's calendar. And David's going to send out a reminder this week of how these payments are made. And the second one is that I know Jim Barber is actually looking to put together our next Society's newsletter. So if anybody wants to send in contributions, Jim would be happy to put these together once he's got enough material. So we can move on to the exciting part of tonight, which is our guest speaker, who is Hongsheng Zhao from the University of St Andrews. I've just heard, I think you were saying you've been and given a talk at Dundee some time ago, so we welcome you back again. And tonight he is going to tell us about testing fundamental physics in astronomy. And again, if anybody has questions or comments that they want to make following Hongsheng's talk, please send them just across to David on the chat line if you are on the YouTube channel, and tune in if you're on Zoom. So I will happily hand over to our speaker for this evening and see if the screen sharing thing is all working well, and looking forward to the talk. So I shall mute mine.
Okay, good. Let me see. Make sure I do a play button. Play from current. Right. Okay. Good. Good evening, everyone. Nice. Nice to have almost face-to-face discussion on astronomy, and I'm sure that's one thing in common between us, and we are passionate about what's there in the dark. Today, my interest is in the dark, in the sky, but even more so in the dark part of the sky. So some things that we can't even tell. Even when it's a dark, clear night, we cannot even tell if there's dark matter in there or not. Okay, so that's the subject of my talk today. I think it's informally I give a title of fundamental physics, but I will give it a more formal title. Will be Tale of Gravity from Rotating Bodies. So. Well, this is this is work done a lot with my collaborator, Engineer Bannock. You probably have had him some time ago when he was a student of me. He has gone to postdoc in Max Planck Institute and came back and to do a postdoc with me. So this is a working collaboration, and once. Much of what I'm talking about are actually taken out from a gigantic review, which I will show you about, eight pages review. We're writing now about this field, and much of it is very technical. I try to take out some sort of a big picture things, and we'll talk about the arguments behind. If there's point, so I would try to leave some point for discussion, but people can come back to me, say, I want to know a little bit more of this and that, which I don't have an animation or something for you, but I'm happy to explain it to you. Okay. A while ago, I came to Dundee to give a talk where my focus was on this thing, the galaxy bar, which is actually shown here in the middle of this picture. And that's a subject I did for my thesis really a long time ago in New York. Time passed, my advisor at that time was having his first son. Now he's retiring, retiring as president of Simon's Foundation. So a good retirement for him. But this is what I did with him back then in New York, about this rotating object in the center of our Milky Way. So picture, so this is about rotating things, okay? And they apparently tell us a lot more about not just the amount of gravitation needed to hold things together in the universe or causing things to expand in the universe, but also it tells us maybe what is causing that gravity is that additional matter in the form of what matter we don't know, dark matter, or in the form of some not fully understood section of gravitation, or maybe it's a combination of the two, that the matter was hidden in the gravitation sector as well. And so to give you my take on this, I think the problem is actually in between these two. So it's not a random mix, but it's actually something we don't fully understand of the gravity sector, which actually has in itself exhibits also both a dark matter effect, but also a modified gravitation effect. I'll give you some evidence to argue for this picture I have. So these things, the amount of rotation will tell us how much the gravity is needed to hold things together. Because as a child, we know that when we take a string and spin it around, yes, and if we let go this pulling force, the string will just fly out. The pebble will just fly out. Okay, see, I'm using a string holding a pebble, and so this effect is a balance that something is rotating, is a balance of impulling gravitation in our case, because there are no strings attached to stars. The only string, if you like, is superstring, gravity. Okay, keeping them in order on orbits. And so there's this balance that you see anything rotating is non-trivial because there are no springs, nothing attached. So that must imply gravitation. And otherwise, the thing will be transient. They should be flying apart, or it should be very rare to see such things. It was just like you were seeing it. The fact that you're seeing these things quite often is holding gravity. Okay, so that's concept number one, which I will come back to. The other concept is can you maintain that rotation? So one thing is to say you have the force to hit, but what if you have ways to dissipate that energy by some interaction with some other matter? Then you might lose that rotation somehow. Okay, so that's the second part, more telling us the source of gravitation. The different ways of providing the gravitation will tend to, for example, leave a signature with the rotation. Maybe it will cause things to keep on rotating as if there's no friction, or there could be that there's a friction, things that start to slow down because there's really some additional stuff floating around, exchanging energy and angular momentum with. Okay, so that's number thing. So the line that I spoke about some time ago was to say that this bar we see in the center of our galaxy, which is American football shaped object, so not exactly disc circular, but actually, like a spindle and rotating around the very black point is the center of a galaxy. And we are somewhere further out, just out, hold on a second. Yeah, we are actually, our position is outside this diagram, further out to actually below this. So this rotating thing actually is quite fast in its rotation. And there's no apparent slowing down because when we go to other objects in the universe, we see bars like this, fast rotating bar. And that is one argument suggesting that there are not enough material to slow it down. Okay? So that is an argument to say that the source of gravitation are likely to provide by directly additional gravitation rather than the matter, rather than adding additional dark matter. Okay. So, and I'll give you further evidences along these lines. And I actually here had a little summary from the review, but the screen doesn't show very much. But I can deal with that later on and show you that the thing in the review. Okay, so let me step back a few things to summarize, to talk about this, how the rotating things tell us about gravity and how we can. Okay. So most, there are many galaxies with a thing. Okay, and so, oh, we lost a bit of time, but so I was saying that we had a whole range of evidence in support of this theory of understanding of gravitation being different from normal. And this is the review I was talking about. And as you can tell, it's page 61, where we make a little table comparing comparing these two scenarios and how they fare very well. And so this is what so we talk about things such as the galaxy bar, yes, and there will be other things like how the friction of the bar and how the tidal limits of the bar, and I won't be able to talk about all the other things, and but if people ask me about other topics, I'll be happy to entertain that. Okay, let me go back to my PPT to do the sharing for the PPT. PPT. Where's the Zoom? Zoom is here. New share PPT. Okay. Okay, wait a second. Here is it. Okay, and so you see this, right? You see this disk rotation. Yeah, so do say something if you don't hear me very well, or I quite like the interacting audience. So although we turned off the video, but I'm very happy if people, stop me for a minute so that I can clarify things. Okay.
Yeah, we're
Okay, good.
hearing you
So
very
yeah,
well.
with me. So
Yeah.
things are okay. I can do this in full screen, just to slideshow briefing card. Okay, so any disk rotating there is a speed of this rotation. Okay, as we said, the faster the speed and the further away is something, the more gravity, the implies a stronger tendency to fly out. Okay, if you weave a very long string around, you will know how it feels like. Okay, so with galaxies, what we find is that the speed of galaxies doesn't really drop off with distance, it stays pretty much flat. And that is very odd, because if the gravity that holds disk together was dominantly made of the stars in the middle of the galaxy, then the further out, this R means further out we go, then the gravitation, according to Newton, ought to drop. Say, it's just like gravitation in orbit, in geostation, must be weaker than here on Earth's surface. And this kind of expectation means things further away from the Earth, the satellites ought to actually move physically slower. Okay, that's Newton's expectation. And we know that's true with such as Neptune's speed around the solar system is a lot slower than Earth is around the solar system. But this kind of thing didn't happen in galaxies. You see, the expectation is the speed ought to drop at this dashed line, and the reality is this flat line. And this been with us for almost for something like 80 years. The data got better and better. This tendency didn't change. It happened with most disk galaxies. And so this begs the question, how come Newton's gravity didn't work in galaxies? It worked nicely here on Earth. The thought is maybe Newton's gravity was only tested very precisely here on Earth, so it's no wonder it didn't really work. And another way of saying it is, maybe it's just working. It's just that the universe could have a little bit more light. There's not a lot of dark. There could be some dark matter before that holds the galaxy together. And we don't see that dark matter, but this discrepancy is the evidence for that. And we see news like this from BBC all the time, that people discovered more dark matter in the universe. And all the dark matter doesn't seem to work very well, etc., etc. What we're talking about is this and related phenomena. But galaxies is a balance. That part is for sure. There is balance of gravitation and the acceleration. It is just what's the budget of this gravitation? This was taken from the earlier review. Okay, so the assumption that around every disk galaxy, there is this fuzz of blue galaxy, blue stuff, meaning dark stuff, actually, otherwise, around this bright disk, okay, which is seen edge on now. I have to show my hand so that you can see me when I gesture. And so this effect, there's apparently introducing such a dark halo apparently explains many things in our universe. In fact, pretty well, not just galaxies, but galaxy clusters and even the expansion of the whole universe. In fact, in the expansion of the universe seems to demand not only this, but also some kind of dark energy in order to do it. So evoking dark things to explain things seems a pretty logical method. Okay, there's one drawback with this is that's not reality. In reality, we just see this yellow part. There's no direct evidence, the orange part, with no direct evidence of this blue haze. That's just our imagination. So far, when we look for particles, new particles, we didn't find such particles yet. And we've been looking, very clever people, spending lots of money, have been looking at this very closely. It could be that we've been looking in the wrong part, and it could be that we need more creative thinking in what these things ought to be. Okay, and this comes to the cosmology part, that you can ignore the rest, but this pie diagram you probably are familiar, that the universe in the standard approach, in order to explain much of the phenomena of the universe, apparently we need at least three different energy forms. Okay, so everything comes out to be energies. Different physics for different creation of different energies, but these energies interact. Okay, what are these three? Okay, the part we understand is the tiny part, is the 5%. That's the energy holding stuff that here we are familiar on Earth. Okay, baryons. From microscopic particles we can find in laboratories, and up to mountains and seas, everything. Okay, the physics is very complicated. We don't understand climate, it's very, but we understand that fundamentally they are just these few particles: proton, neutron, neutrino, etc., electrons, etc., etc. But not much more than that. Apparently, just using this is not enough to explain all the stories. The universe, apparently we need this other 20%, 25% of the pie in some form that we don't know yet. Okay, and the standard phrase for these is dark matter, but also the most popular one is the cold dark matter, meaning just something massive particle, some very, very massive particle, nothing to do with any of the known particles. It's a whole new beast of particles that physicists can invent. They have various motivations to invent them. The drawbacks is, first of all, they're very difficult they are made to be difficult to detect, and so it's a bit of self-fulfilling. So it's made very difficult to detect, and there are no evidence for them. But you would put them there such that word makes sense. Okay. The other part of the even embarrassing question is we need a different form of energy, not in the form of elementary particles, but in the form of dark energy. That is a uniform energy that spread all over the space. It's not clumpy like particles are. Yeah, it's like everywhere. A little bit like the Higgs thing, which is everywhere. Okay, and something else which is everywhere in the universe is you could say photons could be everywhere. There's the light part. There's microwave background everywhere, and there's neutrino everywhere in the universe. Okay, and so this dark energy is like that. It's everywhere. It doesn't really collapse. It's fairly even. everywhere. And it also has a very weird pressure. It's a negative pressure, okay? But that's just to say that is different from ordinary material, which have positive pressure, ordinary energy forms. So apparently, the standard model need to invoke all these two independent elements. And the line of work that me and my postdocs trying to do is trying to figure out a way to connect back to the material we know. For example, neutrino is a quantity we often talk about. It's an elementary particle, which we know exists. It's just that its nature is not fully understood because it's very light. It's just, you know, it's a million times less massive than an electron. So neutrino, they come together. Electron and neutrinos like to come together, but even though the interaction is still very weak, but they like to often they can be created. They can interact. Let's say that's how we discover them. But because they're very, their mass is very elusive. And one of the ideas I've been pushing for is maybe the masses of these was responsible for the weird phenomena of dark matter that we see. Okay, I'll just leave it as a discussion point. I will not go into it. If people like to ask me about it, I will. And this form of energy form, we call it a hot dark matter because neutrino is not as clumpy as the standard model. Okay. And people can ask me later about this viewpoint. But because they have very weird mass, we think they can pretend to be a modified gravitation. Okay, let me get down with, okay, so the motivation that gravity might be weird is not actually just arbitrary, because Newton, for example, when he came up with his theory of gravitation, he's using the fact that that the speed of planets apparently follow some rules determined by Kepler, that they actually falling. And the one way to say this is to invent gravity, which is acceleration here, g here, which goes proportional to the mass of, say, the main body, say the sun, and the distance to inversely to the distance of the object, and with some constant here just to give a nice unit. And this would explain the motions of the planets. Basically, this would balance what's called the centrifugal acceleration of the planets around the sun. And he would explain Kepler's law. But we know that this explanation, while very beautiful at the time, has its fundamental flaw. Is what happens if we make this mass bigger and bigger? We would get a speed, velocity, v here, bigger and bigger. At some stage, it's going to be speed of light. And you come into a contradiction. So how could you, according to the law of Newton, make something faster than speed of light? Which seems intuitively difficult, even if you don't believe Einstein's relativity. You know, how do you make something faster than the fastest thing, apparently, out there? But with the coming of Einstein theory, it's realized that speed of light is really the limit of physical objects as motion, okay? And so that implies Newton's law fundamentally needs correction. So although it's very beautiful in predicting the position of the motion of planets, it needs a correction. And Einstein was right that this correction would have explained why Mercury doesn't visit the same pericenter, that is the closest place to Sun, each year. It actually drifts. That percent actually moves around, and that's due to the correction to Newton's gravitation. That's a speed correction. That is, when Mercury is moving very fast near the center, there's that correction is more important. But there's another correction. In the same time of Einstein, people realized, as Einstein's invention of special and then general relativity, it was realized that our fundamental physics world is not a continuum like Newton sees. The matter just goes from one to the other, and the form of and the matter stays exactly at their observed position. In fact, it was realized that there is a fundamental constant in physics called h bar, Planck constant, that things cannot be in absolute no motion. Okay, there must be some motion, some fuzziness associated, even the most coldest particle. Okay, and that is quantum mechanics. Now, the question then begs to be asked is there intersection between gravitation and the quantum mechanics? So at what stage quantum mechanics correction to gravity could become important? Okay, so that's the motivation we have. Not just the speed correction, but also quantum mechanics. So how do you see this? This is an interesting schematic diagram, how we can think of the space around us, okay? The space around us is a little bit like this last slice here, this big thing, with a lot of, so this is really a slice of space. Okay, you see all this space is not very bumpy here because there are matter here and there. According to Einstein, that for example, if you put a black hole here, the space near there is warped. Okay, you make a distorted shape. Okay, and so space is in our time is certainly bound by matter. But quantum mechanics also says even if these matters weren't really existing, but just some energy forms here, and quantum mechanics says that there is uncertainty with this energy form. The energy form is going to have some fluctuation. It cannot just stay static like that. So if this energy form is present, then it must contract and expand space as well. So space becomes bumpy as well from quantum mechanics. But if you look at the very large scale, we know that quantum mechanics may be not so important. Things are actually smooth. When we throw a stone, we don't think about quantum mechanics but if we throw an electron, we do worry about quantum mechanics because that's very much subject to the little things, whereas when we look at the big thing, we don't. So normally consensus is like when you talk about galaxies and galaxy clusters, this gigantic universe, this gigantic quantum mechanics is perhaps not so important. Okay, that's the gut feeling, but is this gut feeling correct? Okay, have a look. Actually, this may not be so correct. Quantum mechanics, okay. So classically, we think of world as this a little stone rolling in this ball. Okay, this curved surface or ball is symbolizing space, and this stone here symbolizes, say, a planet, say a star inside a galaxy. Okay, it's rotating, and the space is a smoothly but curved band because there's some additional material in the middle, for example, and less so outside, so it's a little bit bent. But that bending seems to be on a bigger scale pretty smooth. Okay, but if you look at it quantum mechanically, there's actually a little bit of bumps everywhere. Okay, these bumps not so important. You know, a ball is not perfectly smooth. Yes, but if you roll it, it's almost frictionless. It goes back and forth. We can ignore that little bump most of the time. But there's a situation where you can't ignore this. That is, if this bump, if the space is very, very flat, like this situation here, then you would say no motion of this little bead, because it's very, very smooth. But in reality, you see these little bumps. Now, because it's so flat, these little bumps actually matters. But when do we, in a situation, in this lower situation, in fact, in galaxies or in space, not here on Earth, very strange. Why? Because here on Earth, we have one massive source of gravity, which is Earth. We're so close to it, the gravity is so strong that the space is already shaped by the material on Earth. Okay? And even in the solar system, this material, this whole space is shaped by the gigantic mass of the sun. But if we go several light years away from the sun, not very far by astronomical standard, just go to the nearby star or somewhere in between, the gravity there becomes totally berserk. It's so small. And it is the typical gravity in the universe is very, very small, about 10, something like 8 or 10 orders of magnitude below here, below what we're used to on Earth or in the solar system. Okay, so it is possible that the gravity works differently in galaxies, actually. And quantum mechanical behavior may be important. These fluctuations may be important. And of course, if you talk about fluctuations, also, there must be a scale, you know, how flat is flat becomes important. It turns out this number comes out all right. The expansion of the universe, that I earlier mentioned, this dark energy expansion there implies an energy density of the universe. Okay, this energy which is everywhere, it comes around to be a number, say a rho, a vacuum. We say, okay, the energy or mass density, mass equals the energy according to Einstein, and by the c squared. So loosely speaking, they are equal, and so this thing is implying that to create this kind of energy density, you need a gravity, strength of gravity, which comes around about 10 to the minus 10 meters per second squared. Remember the G, the 1G here on Earth, in these units would be 980 or nearly 1,000 meters per second squared. So the typical energy in the typical gravity here in the universe is something like 8 orders magnitude smaller. No, the 12 orders magnitude smaller actually here. So, and apparently that number, this number you see here, also you see it in galaxies, is the typical acceleration in galaxy. Give you a factor of 10 up and down, okay? So here comes the picture. So if you look about the energy density of the universe, if there's only this something called dark energy, then it is just everywhere one number, okay? Okay, it is just that one number that's shown by this dashed line. Everywhere is the same. For all the for different strands of so whether you're near the sun or further away, you always have this uniform energy density. Okay. Now, classically, the energy density actually would change depending on how much gravity is in a place. Okay, so if you're near a black hole or near the sun, then your gravity, there is an additional contribution on top of that average due to the universe. You have an additional contribution due to a nearby object, and that's this G. That symbolizes by the gravity of that object. And so the stronger is the gravity of that object, the more deviate it is from zero. So the reality is the sum of the two. Now, the interesting thing is what happens. So the total, you add up the two, this will be the total. Okay, this is the solid line. What happens if you are in a regime where gravity is not that strong? It's sort of in the weak part, in this part of the diagram. So that you're kind of dominated by the dark energy of the universe. Yeah. You are sufficiently far away from any regular object. There, whatever explains the dark energy of the universe, the physics due to that, ought to have something to do with the law of gravity in those regions, in those galaxy regions. And we know that the dark energy, which is everywhere, is responding for the acceleration of the whole universe, must be a quantum mechanical behavior. That must be, because it's not part of our known physics. So a new field is needed, and the quantum mechanics associated with that field must be. So this is implying that in the edge of galaxies, surprising surprise, though this gigantic thing, quantum mechanical behavior may be important, but that quantum mechanical behavior is in the gravity sector, not in the sort of the ordinary material. So a star's motion, per se is nothing to do with quantum mechanics, but the gravity that's responsible for that, the acceleration of that star, can be quantum mechanically important. And if the quantum mechanics is important, well, Newton didn't take into account quantum mechanics in his theory, okay? And Einstein was careful and noticed speed of light is the limit in his theory of gravity, but he did not take into quantum mechanics. And after Einstein, we discovered there is this dark energy around the universe. Einstein even postulated there could be something like a cosmological constant there, but he didn't know its physics. He just put it there. And now we discovered that this thing is there, which demands explanation, most likely quantum mechanical origin. It implies that now we are forced to say that in galaxies, edges of galaxies, we need quantum mechanics in the gravity sector. Otherwise, we cannot explain why the universe would expand, why stars would go around the galaxies in this funny way that doesn't fall with speed. Okay, so this motivates a range of theories called modified gravity, given a particular name called MOND, M-O-N-D, modified Newtonian dynamics, and different motivations for it. This is my take. It is quantum mechanical and only appears in the edges of a galaxy where gravity is sufficiently weak. if we're very close to, say, a sun or something, where the gravity is extremely strong, then the dominant effect is this faint dashed line, not that of the blue line. Okay, so this faint dashed line gets bigger and bigger. Let's go to the right-hand side of the diagram. And so then this quantum mechanical effect is not so important in the solar system. Okay, but it can be important between stars, between us and Proxima Centauri, for example, or between Proxima Centauri and its orbiting companion. Sorry, I say Proxima. So Proxima is rotating around the Alpha and Beta Centauri, and so this is this motion, the Proxima's motion around its center, can be where this quantum mechanical can be important. And we written a paper about this, that in this rotating system, in that world, quantum mechanics can be important in its gravity. And so the magical number is when gravity is weaker than this number, we have something new. Okay, now people have gone through a lot of detail, say, what would gravity be if we make these detailed corrections? And so this is the rule of galaxies that we find. So from a galaxy's rotation, and from the amount of stars it has, and what it ought to, the speed it ought to rotate, we can figure out two quantities. We can figure out, one is the observed gravitation at any point. You know, each is a data point is a certain distance from its center and a certain speed. Here the speed is 120 kilometers, and the distance is 20 kiloparsec. And then I translate to a dot here. Okay, its acceleration there would be, say, this dot. And then from the how much stars there is inside, I can figure out what it ought to predict, the gravity from the baryons. So then I put the dot here. Okay, so if the physics was just, there's no random, there's no rules in galaxies, then I take the next point, okay? I take the next point, and next combination will be a random dot on this diagram, and then another point, okay? I would just get a big mass, dots and dots, okay? But in fact, no. All dots in this galaxy line up to a string of dots along this line with some scatters, because data is never perfect. Okay, very strange. And you say, all right, that's fine. Something going on with that galaxy. Now I take another galaxy, say Andromeda or some Milky Way or something. Then I plot a set of dots. I should get another curve somewhere, say, going diagonally in the opposite direction, say. No, this time again, we see them lying along these dots. So apparently, nature had made a rule as far as these disk galaxies is concerned. Every bit of speed here will almost predict how much. So if you know how much stars there is in this system, how much gas and stars is, you can actually pretty much predict how much the gravity is, or how fast this galaxy ought to rotate. Apparently, this is a bit strange if you believe the concept of some dark matter in some more random, somewhat random distribution around the galaxy. You can have a little bit more, you can have a little bit less. Then I should get all kinds of lines here on this diagram. And maybe one galaxy had a happy life, it goes on this line, but maybe another galaxy had a terrible life, had an encounter with another galaxy, and all kinds of damages done to it. Maybe it's dark matter gone berserk, and then it should go on a different line. No, it still stay on this line. So that's one evidence against dark matter. The spread along here is too narrow. Okay, and so this is work by my colleagues on this. There are many things like this. I don't have to repeat. And they work also for things which are not exactly rotation supported. They are called elliptical galaxies. And here's another catch. It's kind of a joke. Okay, so if I tell you, this is the speed of some galaxy, and I tell you how much stars there is, and ask you how much dark matter you need, and you crunch your numbers, you add dark matter to the appropriate places, voila, you can explain this rotation everywhere, fit nicely. But if this rule of this Mond was right, then you will say, okay, take that star, take the star's distribution, and I would predict its velocity ought to go along this line. Okay? And you see, whoa, it doesn't fit. Observe. But there's a trick on this. So you say Mond is wrong. Actually, there's a trick in this. In this case, it happens the people who are doing the data mixed up. They put one galaxy's speed on top of another galaxy's stars. So it was a fake, impossible galaxy. So this theory, which modified gravitation, is because it was made so rigid, it just cannot, it just says, I can't deal with such objects. But if you just say, take the philosophy of adding dark matter everywhere, you can explain this. So in other words, emphasis is dark matter can pretty much explain any kind of dot combination. I wouldn't say any, but a much wider range of dot combinations due to some, you just give it a nice history of dark matter, just say a story about the dark matter, how it got there, okay? You can explain it. But the thing is, this doesn't, it's not everywhere. It's always along this nice line. So that begs a modified gravitation, this quantum mechanical idea we were talking about. Now, I'll be very quick to go over the some other evidence. I told you early on, I mentioned this bar in the center of the galaxy, which is shown in this bright blue region around this inside in the center of this disk. In this case, you know which way it rotates. It's rotating actually anti-clockwise because the spiral arms are always trailing behind. So the whole thing is ready. Now, if you take the method of dark matter being around, okay, you can put in the appropriate amount of dark matter just to explain this rotation. But you have one, you cannot get away from a drawback. That is, although you set it up nicely in the beginning, that is the amount of dark matter is just about balanced, but as the spinning going on, that this fast rotating bar is going to spun up these dark matter again. And as a result, itself will start to slow down. And this bar will get weaker as it slows down. Okay, as shown by this diagram to the right, the speed actually drops, it slopes down like that. Okay. We can't get around this. Now, this wouldn't happen if the universe was just a matter of modified gravity, it wasn't physically adding some material there to absorb the energy and angular momentum. Then the bars can just keep on going. Now, what's reality? reality is we see bars a lot, and they are always fast. We don't see them for a lifetime, or one bar for a lifetime, but the fact that we see a lot of bars are going fast, very few slowly ones, implies that they have had a happy life, not exchanging energy with lots of other particles. Okay, so that's another form of argument. So it goes back to what I said in the beginning. There are also other type of arguments. This is a work in progress. I did mention Proxima Centauri situations. These are binary situations, two stars moving around each other. Okay. Now, here, if dark matter is right, okay, then you will be surprisingly, the motion will not be speed up by dark matter, because we don't expect stars, individual stars, to be harbored with dark matter. The reason all in between a binary star, a tiny space, to have a lot of dark matter. The reason we don't expect so is stars tend to be formed in a cluster like this, okay? Twinkle, twinkle stars. They were actually from a gas blob which collapses and formed into individual stars. So most of the gravity ought to be from collapsible material. It's like an ordinary stuff, energy which can dissipate energy. Okay, so we don't think in the beginning there was a lot of dark matter to hold it. We can't, if there was, they wouldn't collapse. Okay, so the fact that they collapsed from stars means there weren't such things. So unless you somehow later on plunk some dark matter between two stars, you can mathematically, but that's so ad hoc that nobody accepts. So we will say that the binary star's motion will follow the rule of Newton. Should follow the rule of Newton. Okay, if gravity is not modified. If quantum mechanics was not important. Now, that's more or less true until the point of two stars are sufficiently far away. Then this becomes testing. Then we're not so sure if Newton is right. So what we are doing now is actually gathering the velocities of these widely separating stars, binary stars, including the case of Proxima Centauri system. And their motion, there's a large survey, astronomy survey by the Gaia satellite, and which provides precise motion data, particularly sky motion, not so much the Doppler motion, but the sky motion, proper motions of stars. And we're looking for those very widely separating ones. And we're building the statistic of this. If we find their motion is deviate from that of Newton, say slightly faster than Newton predicts, then that will be a hint that gravity indeed is modified in these scales, sort of larger than the solar system scales. Okay, and the preliminary look on this is suggesting that the velocities are indeed faster, but there are lots of noise causing this, so we need to do more work to get the cleanest data. So stay tuned on this point. And other points we are gathering evidence is on cosmological scale. Say colliding galaxies or colliding clusters, the speed of these things also be higher in our gravity system, but they wouldn't be as high in dark matter system, because when you collide into things, if there is a lot of dark matter around them, they are big puffy things, there's what's called friction. Not the physical friction, but the basically mutual pulling. So speed, they will kind of glue together, okay? But in our theory, there is no such, or not as much such things, or no such things, or such things within a different form, then things can go past each other quite fast. So speed, we tend to arrive at higher speed objects. So in summary, rotating things, be it stars, two binary stars, or be it a galaxy, in our theory, they ought to be rotating quite fast, and they tend to be stably fast. They can keep on being fast. Okay, motions can be fast and can stay fast, and can be fast in surprising places where you don't expect any additional matter. Whereas in the dark matter theory, it's opposite. But there's a range of evidence now speaking that our interpretation is has the chance of explaining these anomalies. Okay, I think I will just draw the conclusion and invite you for questions. Thank you. Are you with me?
Yeah, I'm here. I don't know if June's going to.
I just afraid I draw.
Yeah. I think that was. Hopefully, others will be joining in. That was,
thank you.
Fascinating. June.
Yes, thank you very much, Hongsheng. That is amazing. Thank you. You've obviously got a huge amount of work ongoing with this.
Yeah, it's an 80-page review, so.
Yeah, I guess things like Gaia will provide you with a lot of data for this. So,
yes,
are you using
data of
this?
this sort? Mm-hmm.
Yeah. When you were talking about how weak, gravity is in the universe, when you're inside a galaxy, though, I mean, you have a huge amount of matter, don't you?
Yes.
So between the galaxies, I mean, the space is vast. So the amount, although it's small, must be quite variable.
Yeah, it is. The gravity is very variable, but they are consistently on the small side compared to that whatever we used to here in the solar system.
Okay.
Much smaller, because if you think about it, interstellar space is very, very empty. You know, you shoot a ray, you will not hit a star typically. If you and it's very, very empty because our distance separation from us Alpha Centauri is a typical separation of some light years.
Yes.
Okay. Then the sun's gravity on that system is very, very weak. Likewise, their gravitation on us is very, very weak. And what we're talking about is that weak gravity, actually, we don't fully understand. We understand the strong part. We understand very fast speed, like the speed of light, but we don't understand the very weak gravitation situation in between stellar systems and in between galaxies, and in the intergalactic space. So mass is big, but the distance is even bigger. As a result, mass divided by distance squared, according to Newton. So the distance, after all, is what's causing the gravity to be weak.
So where to next, man? Because I mean, it seems to me that the theories, so much of this is not has no proven data. The business of dark energy, dark matter, has a very theoretical concept to a lot of it. Where do you go next to get the data you need?
Okay, indeed, we can't directly observe these dark things well, we're very limited. You know, some particle physicists say they can, but they still haven't proven that. And so, but we can see how luminous things, stars and gas, how they respond to the gravity.
Yeah.
Okay.
Yeah.
It is that response we can measure. Sometimes we can measure in real time, like maybe a binary star, or we can monitor, for example, we can monitor Centauri system in real time. You just have to be patient. We stare at it for 100 years. It's going to move apart. And we know if the law of Newton is rigorously applicable there. But we need Gaia satellite again, in 100 years' time to get that kind of accuracy. So it's still a little sci-fi at the moment, but in principle, we can nail this problem. Another type of data is we can with statistically. That is what I said about the bars, for example. We look at how the rotating thing, see if the rotation slows down. If the rotation slows down over time, but we can't really see it, but we can statistically see it. We ought to, if it's something slow down, we ought to see some fast ones and some slow ones. Yes, more slow ones. Yes, prevalent. Yeah. But if we don't see them, that means things haven't slowed down. Or unless like everything was just made to deceive our eyes for this instant, that would be very contrived. Okay.
Yeah.
So these are the two strategies we use to break this conundrum of two explanations for the same phenomenon, for roughly the same.
I'm guessing I'm going to miss out on the 100-year data collection, but I think.
Yeah. We hope to speed this up. COVID slowed down things a bit. If this Gaia data was, we're building a larger statistics, maybe in a year or two, we could have sufficiently number of accurate motions measured, all this, that we can see if there is a population. So we can't see individually, we see the population. If we see an abnormally fast population of binary stars, they ought, they are so far away, are separated, they ought to be slow, but they are fast. Then there's a case. But then we need to disprove that couldn't be due to others. They are fast because of other things. And maybe there's a perturber near it, or maybe they all have strange histories or something,
But then the statistics would start to rule out these oddities. Statistically, once you get enough data.
Yeah, as you have more and more data and is more and more careful with analyzing them, it'd be hard to say, all right, they were all just accidentally bad. Yeah. It could be that, there's a for that here. Evidence is going to be indirect like this for a little while, unfortunately. In the meantime, people like myself are making progress in the theoretical side, trying to understand how to make such a theory that such motions are naturally explained. It demands explanation, but the detailed working of the theory need to be spelled out. And that's what draws that's what I'm interested in at the moment.
I can only wish you luck with that lot.
I can show you the piles of mathematical equations I'm playing with.
I fear there might be.
We have a question from one of the viewers on YouTube. Scully has asked about the galactic rotation curve. I think it was possibly an early slide, maybe the second or third slide you showed.
Yes.
You had a galactic rotation curve, but he's asking, why is there that anomalous dip near the center?
Beginning.
Yeah.
In the beginning.
You would expect it to be quite a smooth curve all the way out, but
okay. This kind of thing is not atypical. This has to do with how the ordinary stuff is played, how concentrated they are. For example, if you have a big black hole and the very little stars, very few stars in a large distance, then what happens is you get very close to that black hole, your speed just suddenly goes up. Whereas before it was quite low. But none of this has not anything to do with what's the dark matter stuff, which is further away. So the story I was emphasizing was the story further away, where the gravity becomes weak. And what's happening here, although it's like, speed is a bit low, but actually gravity here is actually quite high. So that's not the main story. So in any system where gravity is weak throughout, say, there's some system called dwarf galaxies. They're weak throughout. The rotation curve is always just a gentle climbing up. And if you have a little bit less star or a little bit of bump of gas, and it will do little wiggles. But it does it in a very predictable way. And so that's also an evidence we think it may not be a problem with just adding some dark matter.
Okay, right. That's good.
Thank you for that question. That's very legitimate.
Yeah.
So different galaxies. So this galaxy does that. Maybe another galaxy doesn't have this bump, but this is a peculiarity of individual galaxies. That's not. We think that's not the main physics. That just says, just like different human beings, they have different measures and different mass and weight. But what's generic is their fifth force far away from them. That's the thing we're talking about. So independent of their shapes, individual shape.
Can I jump in with a personal question?
Yes, please.
Do you think we're approaching another sort of major shift in theories and physics? Because there's your research, which I would call it very small scale, even although it's dealing with stars and planets and within a galaxy. And you kind of hinted at the bigger picture, some of the cosmological things with colliding galaxies. And I've also read a few papers recently about some anomalous findings of very, very large structures, which kind of imply that the dark energy theory may not be quite as. Do you think we're getting to a stage that there's going to be another overturning of ideas?
I think it's just like, the better we understand the standard, what the standard model of dark matter, dark energy is doing, the more dissatisfied we are with it. It's true with everything. We look into details. By and large, it kind of works. But we look in detail, it doesn't seem to us. Maybe there's something richer than that. And this is a repeating theme. Now, I think the standard of dark matter and dark energy has its strengths in where it works. It has a lot of strengths. It's straightforward, and it can sometimes get numbered very precisely. But it's always in a scale, not the ones that we are talking about. They are always in a scale where the acceleration of gravity was very, very strong. So this is no problem. It's just like yes, that theory explains very well that initial dip of that particular galaxy. Okay, let's just say, yeah, let's say it explains here very, very well. Yeah, okay, but not when just when things gets interesting, that's where things not working very well. So we think my personal take is we need a little patch on the standard model of dark matter, a little bit a patch. That patch will auto fix this problem that when gravity is weak, rules are a little different from the standard rules. So they don't have to be exclusive, but it would be a mistake to extend the standard rule all the way to these weak scales. Because we know quantum mechanics must come in somewhere to explain this dark energy. You know, that begs us to explain, you know, out there.
Yeah.
And yeah, that's my take.
Yeah, well, it'll be interesting to see over the next few years how we advance in this direction.
Yeah, I think it's very active. Lots of ideas, and I'm here, of course, a little bit biased to talk about the kind of things that I'm more confident with. But there are lots of different ideas, and I have not done full justice to their strengths and weakness here. But I feel that this strand of theory that we're looking at has something to offer to whatever theory one is looking at. And that's why. Another question? Any questions?
There's nothing else on the YouTube channel. June, you got anybody else on Zoom?
I don't think so.
No, I think we've run out of questions.
No, I think I think so. Yeah. Hongsheng, that was just completely amazing. That is a superb talk, and you know, a very, very difficult talk to put together so that people have a chance of getting most out of it. So well done for that. Well done for that. That can't have been, that can't be simple. But we certainly wish you the very best with, you know, what is clearly a wide range of work that you're about to undertake. And as the data comes in, this could be quite exciting.
Thank you.
So thank you ever so much.
I wish everyone here clear skies next few weeks.
Thank you so much.
Nice winter observing. But keep these questions in your head. It's wonderful looking out there.
Yeah.
You know.
Yeah, absolutely. Yeah, absolutely. And you're so right. You know, all of these concepts and ideas and notions, they just make everything more exciting and more things you want to know about, you know, so it's a fabulous field. We really thank you very, very much for your time and effort, especially persevering with the wretched Zoom lark tonight. That's just
I must apologize for the technical glitches we had.
It takes a bit of getting used to working.
Oh no, that was excellent. Thank you ever so much indeed.
Okay.